Hold on, let me record. All right, so welcome to Beginner Track Workshop 6. So hopefully midterm season is going well for everyone. So in this workshop, we'll implement a linear regression model from scratch using NumPy. So yeah, so this week the workshop is gonna go from 6 to 7 because Professor Kerry Nachenberg, the winner of the last lecture award, is giving his final lecture starting at 7 p.m. So that's the reason of the change. So yeah, here's the attendance code and our feedback form. So yeah, go ahead and save a copy of the notebook in your drive. So I'll give guys like maybe 30 seconds to do that. Yeah, if you want to save your work, make sure to save a copy in Drive, because you can't modify the original version. All right. I guess like give me like a thumbs up whenever you're ready. Let's see. All right, cool. All right, so let's do some imports. I guess also like set the seed while we're at it. All right, cool. So here's our target function. So this is the function that we want our model to learn. So this is just basically a line right here. So here's a quick little exercise. So implement f of x. This should only take like one line. So I'll give you guys like 10 seconds to think about this. All right, any ideas? I guess to get pi, you can do, hold on, numpy.pi. Okay, so Maxwell says return np.pi times x plus 10. So yes. Actually, the semicolon is fine, I think. I think Python will just ignore a semicolon. Yeah. All right, so next, let's add some noise to our target function. So we can do that with numpy.random.normal. So let me pull out the documentation. So basically, numpy.random.normal is gonna give you values from a normal distribution. So the first argument is the mean of the distribution. Second argument is the standard deviation. And the last argument is the shape. So yeah, this is what we have. All right, so let's run that. And then next, let's generate 100 data from 0 to 100 for x. So you can do this with either numpy.arange or numpy.linspace. So I guess I'll give you another like 30 seconds. Okay, so Maxwell set numpy.linspace 0, 100, num equal 100. So yeah, that should work. Let's do that. Oh, wait, did I not copy? Whoops. I thought I copied. All right, so let's plot x and y. So yeah, this is what we have. So clearly there's a linear pattern between X and Y. So we're hoping our model should be able to learn this pattern. And I guess let's see what the shape is. So the shape of X and Y are both 100, comma. So we kind of want to reshape X into like n comma 1. So X should be a matrix. So right now it's a vector with only one dimension. So we kind of want X to be a matrix. So we kind of want to add another dimension to it. So we have to reshape X. All right, so Max, do you have any ideas what how we should reshape X? Actually, I think there are multiple ways to do it. But... All right. So a hint is do X dot reshape. So there's like a built-in function that you can do on any NumPy array. So let's see. So you can pass in the shape basically into reshape. So any idea what we should pass in as parameters? Can we just pass in n comma 1? Yes. So I don't think n is actually defined, but yes, that's basically I think you're on the right track. So you can do -1 comma 1. So this is basically, I think we did this actually earlier, like in one of our workshops. I think Nikhil did -1 comma 1. So this basically make sure the second dimension is a 1 and whatever the first dimension has to be in order to match that. So now X is 101. So yeah. All right, so next we have to split our train and test data and with train test split. So hopefully you guys still remember train test split. So, all right. So I guess let's just start. So what should the first two parameters be? X and Y, yes. And then I guess, yeah, I guess the next parameter is just test size. So let me just do that. Let's do 0.2. And random state. Let's do 42. So shuffle is default to be true. So I'm just gonna leave that, but yeah, like I think making sure shuffle is true is pretty important. So let's do this. All right, so next, before we actually like start doing coding up the class, so let's do a brief review of linear regression. So here's our hypothesis in matrix form. Here's our loss function. Here's the gradients, and also in matrix form. And last but not least, we have our gradient descent update rules. So yeah. So all right, so now we have our linear regression class. So this is basically the bulk of the guided project. It's just to implement this class. And then we're gonna try to like apply this to some data. All right, so let's go through this class together. So the constructor here takes in 3 parameters. So num epochs is just the number of epochs. LR is the learning rate. Verbose will create a plot of set to true. So this is useful for debugging. And then as for attributes, we have epochs, which is number of epochs, alpha, which is the learning rate, verbose. which is the same as the parameter. Weights, which is the weight of the model. Bias, which is the bias of the model. And we have, last but not least, we have losses, which is a list containing the loss of each epoch. So you can sort of think of this as your loss history. So yeah, there are, I think, a few methods. So first one is predict, which is pretty self-explanatory. It makes a prediction using the hypothesis. So it takes in one parameter, which is the data, and returns prediction. So yeah, this should only take like one line. And next we have the loss, which computes the mean square of the current prediction, takes in two parameters, targets and the predictions, and returns the loss, which is a float. And next we have grads, which computes the gradients of the loss with respect to the weight and bias. So it takes in three parameters, the data, targets, and predictions, and returns grads, which is the tuple containing the gradients. And last but not least, we have fit, which pretty much fits the model to training data and targets. So it takes in the data and the targets, and it returns a reference to self. So yeah, the reason it returns a reference to self is just because of I'm just trying to follow the scikit-learn's API for linear regression. So yeah, you don't have to return anything, but yeah, so this is basically what this line does. So yeah, so all those, every to-do comment is followed by a line that you have to like edit. And I'll actually encourage to not edit like any other lines, because that might introduce some bugs, because this code has been pretty like well tested. So yeah, I guess there's only one of you today, so I was gonna encourage you guys to work together, but since there's only one person, I guess that'll be kind of awkward or difficult. Okay, so yeah, I guess Maxwell, if you have any questions, definitely let us know, or if you're stuck. And also, like, okay, let me also go through some useful functions that you might need. So okay, let me make a NumPy array. All right, so the first function that you might find useful is numpy.sum. So this is gonna return the sum of the vector. Next we have numpy.average, returns the average value of the vector. And then we have, let's see, numpy.dot. So this returns the dot product of this vector. Or if the arguments are matrices, so do the matrix multiplication of those two matrices. So this is the same as the @ operator. So the @ operator also does the dot product or matrix multiplication. However, this is different from the asterisk operator, which computes the element-wise product. So yeah, I think these are all the functions that you'll need for, I guess, the guided project. Or yeah, I guess, let's see. I'll give you guys maybe like 20 or 25 minutes to do this. And I guess Max, if you finish early, then definitely let us know.
Or if you have any questions too, that works. Yeah.
Oh yeah, Max. So I guess if you finish like a function, you can definitely let us know. So we can start like, I guess you don't have to like finish the whole class before like letting us know. We can do like all the functions like step by step, I guess. Um, so we're using model.predict. You mean in the fit? Yes. So in the fits, you should like, so all of these lines you should be calling, or at least most of them, you should be calling like other methods. So for example, like in the main training routine, we're making predictions. So you should be calling the predict method from earlier. So I guess the way you could do that is okay, like so in order to like I guess call a method of the same class in Python, you have to do self.predict. And then let's see. I think it's just one parameter. Okay, yeah. X. And also if you want to refer to any like attributes, you also have to add like self in front of that. I guess like all the other variables without the self is just like, I guess, temporary variables. They're not like class attributes. All right. Hope that answers your question. Okay, so what function should we be using to implement the predict method? All right, so that's a good question. So our hypothesis here is, as you can see, involves some matrix multiplication. So you can either use numpy dot, or you can use the at operator, which also does matrix multiplication. So yeah, our data is a matrix, and our weights is a vector. So yeah, we can multiply them together with matrix multiplication. And I guess you also need matrix multiplication in the grads function. So predictions equals x at self.weights plus self.bias. Yes, exactly. So yeah, I think this is actually the correct answer. So good job. So yeah, all of these should be like 1 or 2 lines. So if it takes more than that, then maybe you're taking the wrong approach. Also, if you're like stuck, then definitely look at our equations up here. These are pretty useful. Oh, I guess the two so like here there's like a transpose symbol. So to transpose let me give an example. So to transpose like a matrix, you can do like x dot t. Okay, wait, that's not very helpful. So yeah, so as you can see, x is originally 100 rows by 1 column, and now it's 1 row by 100 columns because we have transpose x. So yeah, this might come in handy in one of our functions. Okay, so Maxwell says for a loss does this work? MSE calc equals 1 over self dot epochs times numpy dot sum losses. Oh, I see. So this is mostly correct, except wait. Except the n here is not the number of epochs. This is like the number of samples in your training data. So epochs is something different. So the number of epochs is like the number of times we want to like iterate through our training data. So for each epoch, you iterate over your training data like once. So okay, let me paste this. So yeah, this should actually be x dot shape sub 0. So this gives you like the number of entries in your data points. So or in in your training data. But yeah, that was a. Oh yeah, wait. Why is this losses? So actually it should be y minus y hat. Okay, so I think I see where confusion is, because yeah, losses is basically just for like storing the loss for this plot here. So yeah, so if you remember from the
also
equation up
important
here.
remember to square the losses.
Oh yeah. Or I guess you can also do like numpy dot average. In this case, you don't need this. So yeah, this is basically this equation up here.
Does that make sense? Next one. Or get any questions about that? Okay, cool. Yeah, no worries, no worries. That's good. Yeah. For a lot of these functions, the passing parameters are like the things you use like the most. So yeah, definitely important, like you notice, to keep track of those too. Yeah, cool. Yeah, it's just
so yeah,
dot,
transfer
dot
is
T.
just a dot T. Or I guess you can also do numpy
You can
transpose.
yeah. That's a lot of words.
Yeah.
A lot of letters. Yeah.
So it takes in an array-like object, and then you can also like specify the axis. That was probably overkill. Let's see. Maxwell said something. So for DW, does this work? So you have, let's see. Let me copy this. 1 second. So let's see. DW equals 2 over x dot shape sub 0 times x, dot shape. So you only need the shape here. So it's just x dot transpose, I think. Yeah. And also you need to do matrix multiplication here. So this should be an add. So yeah, this should work. It's gonna put parentheses just in case. And you can also use n here, because I think they're just the same. So n is y dot shape sub 0. All right, so that was pretty close though.
Just remember, whenever you have like two vectors, yeah, you get to multiply them with like the at or
Or numpy dot dot.
Yeah. Yeah.
I think there's only like two places where you need to do matrix multiplication. Okay, so how about this for dB? dB equals 2 times numpy dot average y hat minus y. Yes, that is correct. Okay, so yeah, I think we're done with all the math. So
yeah.
I guess all that's left is these 3 lines. So yeah, I guess I'll let you figure it out. I think we're doing okay on time, so.
Yeah, I think we're doing good.
So yeah, for the loss and the gradients, you should be calling the methods we defined earlier. And I guess for the updates, you can just do like, okay, so for loss equals self dot loss y comma predictions. I believe this should be correct. Double check. Okay, yeah, that's correct. Gradient dwdb equals self dot grads x comma y comma predictions. Yeah, I believe that's correct. I guess all that's left is the gradient update rule. Which is right here. Let's see. Self dot alpha times dw and self dot alpha times db. Yes. Let me copy this. Okay, yeah, this should be correct. So okay, now it's right. Okay, let's see if this works. I guess let's create a model and try to fit it. Regression. Let's actually set where both to be true and see what we get. Like it's going to fit. So this has the exact same interface as the scikit-learn model for linear regression. So that's actually kind of one of the intuition behind like how this class is written. So yeah, this gives us a plot for the loss. So this is the main reason why we have the losses attribute. So this is just for creating this plot. So as you can see, the loss is originally like 30,000, which is pretty high. And then it goes all the way down to close to 0. So yeah, that's a pretty good indication that our model is doing what it's supposed to. And then we can check out the weights. So I believe the slope should be something close to pi, which it is. And the bias is 0.65. So this is kind of far away from 10, but it's actually not the worst. All right, so next let's make some predictions on the test data. So I'll give you guys like maybe 30 seconds to think about this. All right, Maxwell said linreg.predict x tests. Yep. Okay. So I guess here's a pretty good question. So which R2 score do you expect to be higher? The train R2 score, the test R2 score? Hopefully before you run the cell, you can answer this. The train probably, yep. So yeah, the train R2 score is better. However, the test R2 score is a better estimate of how well the model will do on like, or how well the model can generalize to unseen data. Whereas the train R2 score is kind of like, I guess, inflated because basically the model has been trained on the train data. So that's the reason. And I guess the next cell just generates a pretty nice plot. So the blue data is the train data and the orange data is the test data. So I'd say our model did a pretty good job on this simple data sets. I guess next, let's look at the effect of different learning rates. So this code basically just, so we have like a bunch of different learning rates here, and then we're just training a model on each of them. So yeah, this, so basically the takeaway here is like, if the learning rate is, the higher the learning rate, the faster the loss decreases up to a certain point. So after, if the loss gets too big, then it'll actually start diverging. So let me see if I can give an example. Actually don't know what it's doing. Let's do like, it should be pretty big enough for it to diverge. Yeah, so yeah, this starts diverging to infinity. So yeah, this is what will happen if your learning rate is too big. Okay, what was the original value? I don't remember. Whatever. I think I just broke it. It's fine. All right, so next let's apply our model to a real world data set. So we can do this with load Boston. Let's first run this cell. And let's actually look at the documentation this time. So the Boston housing price, or the Boston data says on the housing prices in Boston. So remember actually like the example on housing prices in, I think, the linear regression workshop. So we're coming full circle back to that in this workshop. So there are 506 instances. So that's the number of data, and 13 numeric or categorical features. And the last feature is the target. So that's the median value of owner-occupied homes in thousands. So this is what we're trying to predict with our model. So let's actually look at some of these features. So first we have CRIM, which is the per capita crime rate by town. So I'm assuming this is going to be inversely or negatively correlated with the median value of the housing prices. And let's see. Okay, here's a good one. So Chas is actually a Charles River dummy variable. So this is actually, I think, the only categorical feature. So this feature will be 1 if that house is close to the Charles River in Boston, and 0 otherwise. Let's see. Okay, this is a good one. So RM is the average number of rooms per dwelling. So I think actually like somebody came up with this with in one of our workshops. So I think someone said like number of bedrooms or number of bathrooms or something like that. So this is pretty similar to this feature. All right, let's move on. All right, so next, let's store our Boston data set into a data frame. So this is like the only pandas part of the workshop that we actually need from last time. All right, so something in chat. Use pandas.dataframe, yes. As we can do like a quick refresher if you need it. Pandas.dataframe takes in data, which is a NumPy array or any like, I guess, iterable objects. And I think the index is optional. I think the columns is also optional, but we're gonna need like one of them. Let's see. Only thing is I don't know how to set those labels. Yeah. Okay, yeah, that's fair. I guess the only thing we really have to do is just, okay. So yeah, so Boston data has like a few attributes. So one useful one is the feature names. So we kind of want to set this as the column. So I guess it'll make more sense when we actually like do it. So yeah, the data should be just Boston data.data. So this is the actual data. And then you can also set the columns to be the feature names. Let's see how this turns out. All right, so as you can see, this formats our data pretty nicely. So the rows corresponds to each instance. So yeah, each row here is a house in Boston. And then each column here is like a feature. So yeah, this actually formats the data pretty nicely, not gonna lie. All right, so next let's check for any like missing values. This is pretty important if you're collecting your own data. So you can't do this with like pandas.isNull, and then you pass in the data frame. And then this basically gives you another pandas data frame with all Boolean values. So what you can do is you can call the any function. So the any function will return a pandas series. So if any of these columns have a null value, then it'll return true. Otherwise, it'll return false. So that's what the any value or any function does. So yeah, as you can see, there's no missing values, so that's good news. But if there's any missing values, you can also like, I guess, replace them. I think I actually did that in the last workshop, but yeah. All right, any questions? If not, let's store the data into X and the targets into Y. So there are actually like two ways to store the data into X. The first way is just to get it from the Boston data set. The second way is to like cast this data frame into a NumPy array. So as you can do it both ways. All right. Any ideas how we should do this? For X, numpy.array Boston data.data. So yeah, actually you don't have to call the NumPy array on this one. So you can just do like Boston data.data. So let's check the type. So this is already a NumPy array, so you don't have to do that. The second way to do it is just to do NumPy or NP array. And then you pass in df. So this also works because df is this data frame here. You can cast this back to NumPy array. So yeah, okay. All right, so I guess what is y then? Let's see. So there are a few attributes to choose from. First one is data, which we use already. Second one is the documentation. And then we have feature names and file name and target. I'm gonna guess target for target's law. Okay, yeah. That is a very educated guess. All right, so next let's do train test split. So this is exactly the same as we did earlier. So I'm just gonna do this for you. And then next we can fit our model. So this is gonna take a little bit to run. So just bear with me. So you can also play around with the number of epochs and the learning rate. Okay, so this is a good question. Is the scikit-learn one more optimized, or would it take just as long? So I think the scikit-learn model actually like does this a little bit differently. So it uses the closed form solution of the linear regression that we discussed, or I briefly mentioned it, I guess. So it uses the closed form solution. So let me see if I can find it. Let's see if I can find this. So yeah, it uses this equation. So all it has to do is to compute the transpose of x times x, and then there's the matrix inverse here, and then yeah, so this is gonna go pretty fast because our data is pretty small, but as the time complexity will be like greater if the data set is like pretty substantially large, and because like we're doing like a million epochs, so yeah, this is gonna take a while to run. All right, so yeah. All right, so our R2 score is 0.612, so that's actually like pretty decent for our first try. So let's actually compare our model to scikit-learn's model. So this is kind of the moment of truth. All right, so the R2 score that scikit-learn got is 0.669. So I'd say we did a pretty decent job. considering this is our first try. And also a solution that the scikit-learn model gives you is going to be optimal because of this equation. So basically did it instantly. And the reason is because, use the closed form solution. So it runs pretty quickly because our data set is pretty small. So I guess here's a bonus challenge for those of you who found this to be a little bit on the easier side. So you can try to implement an adaptive learning rate for our model. So there's a useful article that you can check out. So I'd say definitely look at our prop parts. I think it gives you a pretty, let's see. So basically figure out what's so it looks at the sign of the last two gradients and basically figures out like whether we're going the right direction, which is if they have the same sign. So you should like accelerate or increase the learning rate by a little bit. Or if they have different signs, that means like you're going the wrong direction. So you should decrease the step size. So this is like a hint that you should use. Or if you have like, I guess a better idea, you can also use that as well. So this is basically the end of the first scatter project. So hope you guys had some fun. So thank you all for coming. I guess remember to fill out our feedback form, which is I guess up here. So hopefully you guys have a nice week. And I guess we'll see you guys next week. Stop the recording.
Yeah.